Good evening, everyone. I welcome you all for this day three ACT sponsored faculty development program on next gen VLSI and semiconductor systems integrating machine learning for intelligent design automation. So, today also we'll have two sessions. The first session will be taken by the eminent speaker, Dr. Shivam Verma, Assistant Professor, Indian Institute of Technology, Varanasi, on the topic Ferroelectric FET based neuromorphic computing. I welcome you all on behalf of our management and my own behalf, and I welcome our resource person, eminent speaker, Dr. Shivam Verma. Welcome, sir, and thanks for accepting our invitation, sir. I invite Ms. Senthil Priya to introduce the chief guest, resource person. Over to Senthil Priya.
Thank you. Thank you for inviting me.
So, good evening, one and all present here. It gives me immense pleasure to introduce our esteemed resource person, Dr. Shivam Verma, Assistant Professor in the Department of Electronics and Engineering, Indian Institute of Technology, Bhubaneswar, Varanasi. Dr. Verma is VLSI design and nanoelectronics with a strong research focus on spintronics and non-violent memory and logic circuit design. He obtained his PhD in IIT Rocky and his work on spin transfer torque based memory and logic design contributed significantly to the advancement of emerging device technology for low power VLSI system. Sir, before joining in IIT Bhubaneswar, Dr. Verma was involved in several academic and industrial collaborations focusing on next generation semiconductor devices, energy efficient circuits architectures, and VLSI system integration. Sir has published numerous research papers in reputed international journals and conferences and continues to guide many young engineers in the domain of advanced semiconductor technology. We are truly honored to have Dr. Shivam Verma with us today for the session to share his valuable insights and expertise. With this, I welcome you, sir. The session is over to you, sir.
Okay, thank you for this wonderful introduction. Okay, so let me share my screen. So my screen is visible?
Yes, sir.
Okay, and do you see the slides moving? Yeah, so yes, slides. I hope the slides are moving.
Yes, sir. Slides are moving.
Okay, fine. Thank you very much. So yeah, let me start with this lecture. And so briefly, I will start with the background of neuromorphic computing. And then we will move towards how ferroelectric FETs, FEFET, which they are used in neuromorphic computing and why they are important from the perspective of neuromorphic computing architectures. So yeah, this is a new evolving field in this particular, we can say, computing paradigm that is being developed in the recent years. And so yeah, so first of all, you can see the picture on my slide of a human brain. So neuromorphic computing is quite related to our human brain. So as the human brain performs computation using spiking networks consisting of neurons connected through synapses. So we will see how what is neuron, what is a synapse, and all these terms which are involved in this particular presentation and lecture. So neuromorphic computing involves mimicking this biological approach of a human brain to achieve computation, and that's why it is called the next generation computing paradigm. It mimics the behavior of human brain for computation. So the traditional data storage options, they do not have the ability to remember the voltage applied, and for the synapse application. And that's why we are looking at ferroelectric FETs and other emerging non-volatile memory technologies for this particular applications. So yeah, so I hope that I have just briefed you about the what is neuromorphic computing, and let's dig deeper into this aspect. And for those who are not familiar with the conventional computing architecture, let me go through the conventional computing architecture. So this is the computing architecture. You can see in my slides, I have this, yeah. So you can see in my slides, let me show the pointer. So you can see in my slides that the conventional computing architecture is consisting of a large number of cores in the processor. So here you can see this dotted box. This dotted box basically represents a processor chip. And inside the processor chip that is present in your motherboards or computer motherboards, you will find that inside the chip, we have several cores to enhance the parallel processing, or we can say for the parallelization of running an application. We use several cores. Cores are basically independent processing in the units inside the processor, which run a task in parallel. So these cores, they have some dedicated memory that is called as L1 instruction cache and L data cache. So you can see the label here. So L1 instruction and L1 data cache, these are part of the core of the processor. And here are several cores which are there in the processor. Then they are connected to the what is called the second level of cache memory, which is the L2 cache. And L2 cache is is also non-volatile. Sorry, is also SRAM based. SRAM, yeah, for those who do not know what is SRAM, SRAM is a static random access memory. And this is a CMOS based memory which we use traditionally in computers. And this is, you might be knowing about the 6 transistor based SRAM cell. So this is the same that we are talking about here. So if you see that after that L2 cache, we have another level of cache memory, which is called the L3 cache, or we can say this is embedded DRAM, which is a faster version of DRAM that is used for we can say storage inside the processor itself. So together with this, we say that this all is inside the processor chip itself, and all three levels of cache memory, and of course the processor cores, which are independent computational units. So now this processor is then connected to the main memory. Main memory is also DRAM. This is slower than L3 cache, but this is not embedded inside the processor, and it is outside the processor, which is controlled using the memory controllers. And then we have the peripheral controllers to control the peripheral or secondary storage. Secondary storage are hard disk drives, or we can say the RAID or secondary storage, the hard disk drive and flash memories. And then tertiary storage is a RAID memory that is used for server processors. So all these memories are there, at least not the tertiary storage, except the tertiary storage. All these memories are there in your computer nowadays, or in your laptop that you are using. So you have the memory hierarchy on the right. You can see that this is like a pyramid, or we can say triangle, where we have inside the core you have ALU flip-flops, registers, and then cache of memory L1 of L1 nature, which is all L1 cache, which consists of instruction and data. So there is separate L1 instruction cache and data cache. So this has typically the access time of zero point 0.1 nanosecond, less than 0.1 nanosecond. To then you have inside the core or processor itself, we have L2 and L3, which are also SRAM. And then the main memory is also part of the the processor is embedded DRAM. So L2, in fact, L3 is a DRAM. So this L2 is SRAM, and then we have the main memory. Main memory is DRAM, and then we have the secondary storage. So you can see the access time is also increasing as we move downwards here, where the cache memory has L2 and L3 have a access time of 1 to 10 nanoseconds, and the main memory has access time of 10 to 100 nanoseconds. And typically the secondary storage has the access time of 0.1 to 100 milliseconds. So if you see this memory pyramid, you can understand that why it is there. This is basically a trade-off between the speed and the cost. If you see, the cost per bit is very high for SRAM, and the cost per bit is very low for secondary storage, like hard disk drives and the flash memory that you use in your solid state drives that you use in your computers. So speed is very important, because inside the core you need access to the data faster, but also the cost of that memory is very high. So SRAM is very costly, and DRAM is has cost which is in between the non secondary memory and the SRAM. So basically, memory hierarchy is made up of some fast and some slow memories. The fast memories are also costly, and the slow memories are also are less costly. So we involve the slower memories because there are two things that are important here. One is called non-volatility, and the all, if you see this, except the secondary storage, all other memories which are above, or you can say in this part of the pyramid, they are all volatile in nature. So DRAM, as you know, DRAM is basically also CMOS based memory with one transistor and one capacitor. And secondary storage can have magnetic hard disk drives, which are non-volatile, and also the flash memory, which is non-volatile. So we have the volatile and non-volatile memories both in this system. But the non-volatile storage is important because you need that particular storage to keep your data when you turn off your computer. And in the process of booting the computer, you see this change where the operating system is loaded into the computer, and it takes some time to load the applications. So that is basically done during the process of booting. So that is where the data from the secondary storage is transferred to the main memory, and then you can start using that data in your applications. So yeah, this is a typical computer architecture. This is also called the one human computer architecture because this has been used, and so this has been used from a lot of we can say for a lot of time now. And we see they say this is a one human architecture, and there is a separate memory and CPU, where we can say that the data is stored inside the memory, and the addresses are given as input to the memory, and then the CPU performs the computation, and then it is also connected to the IO devices like the display and monitor, and also your mouse, keyboard, and other devices. So this is the computer architecture that you know, which is also known as the one human architecture. This basically suffers from the big problem, which is called as memory wall. Memory wall. What is this memory wall stands? Memory wall basically says that there is, we can say, a data transfer that is required between the processing unit and memory, and that processing unit and memory uh, are sitting at different places. CPU is a particular chip, and the memory is a different chip, which is present on your motherboard, and the buses are connecting these two chips, and these buses they are slow, and they require the data transfer has to be done, and that is quite power hungry. So you require power to transfer data from memory to CPU and then back to memory to store it. So this is what is actually plaguing our computer architecture. Because of this, we need to change because of this memory wall problem. Why this problem is important? Because of the different reasons that I am going to tell you in the next slide. So because of the power consumption or sheer time taking latency of this particular data transfer between the memory and the processing unit, this is very important that we change it. So basically, if you see the data, so about power consumption in 2023, the Information and Communication Technology (ICT) that makes up approximately 10% of the global energy consumption, which is obviously around 2 to 4% of the global carbon emissions. Now, it is important to understand that as the data is increasing, you actually are gradually increasing these emissions and the data requirement. So a lot of the data centers nowadays, you are using the AI applications like ChatGPT, and there are many more. So people are basically generating data by the hour, and that data has to be saved. You are taking pictures for wherever you go, and people are making videos, and they're transferring data at will. So basically, this has to be managed by the industry, and in order to meet that growth, we basically go for the GPUs, which are used for machine learning applications, and big servers are required to that run these GPUs, which basically require a lot of power. For example, this NVIDIA DGX A100, it requires 6,500 watt of energy, which is very high. So you can see 6.5 kilowatts of power is required. And the idea of neuromorphic computing is to take the inspiration from the brain, which we know is power efficient. So as the applications are getting bigger, so you know that you require more and more computational power, and we also do not want our computations to be power hungry as GPUs, because GPUs are where the huge amount of infrastructure like data centers are required, and the management of those data centers, and of course they are going to take a lot of power. So we need some energy efficient solution. So that is what is important. So idea of human brain and using neuromorphic computing, how the brain does computation is very important, and it is easier to, we can say, uh, is from perspective of we can say the rate at which we are generating data, and to manage that data we have to go for this modern computing architecture. So basically, if you see the human brain, it works at less than 20 watt. Then you have the B brain, which is basically it works it's a 10 microwatts, which is significantly smaller. You can see, and then that you have IBM Synapse, which is a neuromorphic chip. This works at around 70 milliwatts. So you need neuromorphic computing, which is more power efficient uh, to manage the continuous growth in AI and machine learning, and data centers that are required to, or we can say, perform your restore your data that you are continuously generating. So the standard computer hardware has a lot of limitations. You can see that as you have reached the physical limits of Moore's law, and the clock speeds stopped increasing in 2004. So you cannot increase the clock speed any further. It means you cannot speed up the data transfer between the memory and the CPU. And also you cannot go for transistors beyond physical limits, so you cannot decrease the power also. And bandwidth is the main bottleneck that is there between the network and the memory, or you can say that the transfer between the memory and the CPU. So you have to go for some alternate architectures, and those architectures basically are important to. We need noise robust computation, and allow aggressive optimizations. So we need systems which are noise robust and they do not run with high clock speed. And we can so we can look for neuromorphic computing that addresses these issues. And one of them is basically advantage is that memory and compute are co-located, in which reduces the bottlenecks in neuromorphic computing. So in any neuromorphic computing architecture, we do not have separate memory and compute units like we have in the one Neumann architecture, and we use they are co-located, they are at the same place. And algorithms, we need algorithms that can do computation using neuromorphic architecture. And because there is a lot of noise in the brain also, so it is important. And the brain is inspired computing is analog in nature instead of digital. So there is still a lot of work to be done in this area. And we are also seeing the very often the bottlenecks for accelerating the memory bandwidth. And it is very important that we try to go for modern architecture, but we also need to optimize it further. So let's see, I mean, how does neuromorphic computing or how does human brain perform computation? It is important to understand. Let's see that now. So biological neuron, basically human brain performs computation with the help of neuron and synapse. And what is neuron and synapse? That is very important to understand. So if neuron is like any other cell in our body, and it has a fatty membrane and which separates, we can say, the inner contents from the surroundings. And then we have inside we have fluid, which is called as cytoplasm. And in this, basically, you will find things which are found in other cells, like a nucleus containing genetic material, which sits in their main cell body, or okay. And but unlike the other cells in our body, the neurons act as information processing units. They receive inputs from other neurons via their dendrite tree. So there is dendrite tree. So you can see this these cells have especially made for this information processing. They have dendrites, and then the signal from other neurons, like from muscles, glands, they transfer it via axon. So there is axon, which is also connected to we can say neuron. And then we have the linker, which is basically we often use neuron in this way. And they are very important to we can say to understand from the perspective of neuromorphic computing. And the connection between the joint here, this is called synapse. The connection between a neuron and this axon, there is a small gap. This is called synapse. This is where the memory, we can say, data is retained in our brain. So that is used for computation. So this is just an overview of what happens inside a human brain and what is neuron and what is synapse. So you see this small one that is called synapse, and this blue one, this is called neuron cell. And then of course there is a connection which is called axon that is there. And at the end of axon you have what is called synapse, which stores the information. So these are the important things in a human brain, which are part of the computation that the human brain does. So yeah, it is similar to artificial neural networks. Artificial neural networks, basically, if you have learned about machine learning and ANNs, in ANNs, what happens is these translations are transformations are realized by units which sum their weighted, we can say, inputs and pass them through. So if you see that there are inputs to a neuron, and they are different. They are weighted and then they are summed over this, and then they are connected to an activation function. So this is what makes up artificial neural network. So here the computation is based upon weights and biases. Okay. So similar to that, the spiking neural networks are, we can say, third generation of neural networks, and the spiking neural networks are the ones that mimic the brain exactly, and we use the artificial neuron in such a way that we can do the machine learning operations. So if you see this this neuron has n inputs. For example, any artificial neuron, what we model this neuron. So this artificial neuron has uh, n inputs from x1 to xn, and this is has we also call it inputs as activations, and these activations have are with weights w1 to wn. Okay, so which we multiply with the activations to which are summed over, and some of the inputs are then passed to through some function which is called the we can say activation function or nonlinear function, and various functions are used. And in the older works that are on machine learning, and we use the sigmoid function, and we nowadays we use the rectified linear unit or ReLU, which turns out to be easier to work with and gives results which are often better. So yeah, so this is what is an artificial neuron in machine learning and artificial neural networks. We use sigmoid, we use ReLU, and we use this kind of an output is used. So you have so this kind of output behavior of a neuron. So this is the artificial neural networks. Now, biological neuron is slightly different from this artificial neuron that you are used, but this can be implemented only in the software. This may be implemented on a computer, but how do we implement a neuron in hardware? That is going to be important if you want to realize the computer architecture using that is getting inspired from human brain. So we need to mimic the biological neuron. What is biological neuron, which is slightly different? This um so let's talk about that, because here you can see that there's no time dependent factor. So that it is important to understand that the time is also important, and how the biological neuron works is very important. So biological works in a different way. If you see that the the membrane potential of a biological neuron is important to understand. So we saw that in previous cases, the neuron receives input current and it pushes it above threshold that basically leads to an action potential. So which is also called a spike. So each neuron works like in the form of spikes, right? We instead of using artificial neural networks, the brain uses the spiking neural networks, which are the third generation of neural networks. And here the spikes and the temporal, it means time varying spikes are there, which basically are input to the neuron. Instead of activations, you get activations from in the form of spikes, and these spikes are going to change the membrane potential of a neuron. So as the membrane potential, as a spike comes, if you see, this is the resting potential. If you see this particular where my pointer is going now, this is called the resting potential of a neuron. And if the spike comes from any input, for example, there can be n inputs, and if the spike comes, then there will be increase in potential like this. And if the next spike comes, there will be another increase in potential. And when the spike is not coming, the potential starts to decrease like this. You can see the potential decreases. And as the spike comes again, the potential increases, but it starts to decrease towards the resisting potential. So whenever the spike does not come, the potential drops towards the resisting potential, which is this one. So as the spikes keep on coming, finally what happens if you go above the threshold, if you see that this if the threshold if the membrane potential increases above threshold, then the spike is fired and you get output spike from a neuron, and this output spike is an effect of the input activations or input spikes that have been there, and then the neuron resets membrane potential to its initial, or we can say, resting potential. So this is how a neuron works. You can see that this kind of behavior is uh, is is not present in artificial neural networks, but in spiking neural networks you have this kind of behavior. So how to mimic this spiking network or spiking neuron is important to understand. And if you see traditionally, this is also called as integrate and fire neuron. So what is happening is basically you are basically as the voltage will get integrated over time, and the spike comes, the voltage gets integrated. If you see here, this spike comes, voltage gets integrated. The voltage increases, voltage increases, and becomes above threshold, then the potential increases, and then there is a spike at the output, and then you get the resting potential. So this is we can what is called as integrate and fire model. So integrate and fire model of a neuron is very close to a neuron, but not exactly neuron-like, because still you don't have what we call it as decrease in potential towards the resting potential. So here you can see that there is a decrease in potential towards the resting potential. Once the spike is not there, the potential goes towards a resting state. But in integrated fire neuron, you don't have a resting state. I mean to say, the potential does not go to the resting state. So it is important to see that this behavior is not exactly mimicking the entire uh, spiking neuron. So to mimic a spiking neuron using hardware, you need something else, and that is where we have to say that there are three properties to mimic. One is called the weight. When the weight comes, the potential, or we can say membrane potential, V updates. So if the input weight comes from Wi input, then that is added to the membrane potential and it gets updated. So membrane potential should update. Then the second property is called threshold, which is once the voltage goes above threshold, which in this case is, let's say, 1 volt, then the spike comes. So then the output spike comes. That is the second thing. So this is called integrate and fire. Then one more thing that is important is reset after integrate. So it resets after integrate. So that's why it is called as integrate and fire neuron. The only thing that is missing here is that the potential does not decrease to the resting potential, and that's why we have to see what to modify it, and that is where the newer model, we can say, came into picture, which is called a leaky integrate and fire neuron. Leaky integrate and fire neuron, it basically continuously evolves over time, and it has this kind of an equation where as the we can say the membrane potential with respect to time is proportional to its negative of V, which is the membrane potential. So if you see in this case, when the spike comes, when we can say it has only one solution, which is basically Vt is equals to V naught exponential minus T by tau. So as the spike comes, now if you see, the the potential will start to decrease. Potential will start to decrease. Potential will start to decrease, and that's why you need this kind of behavior, which we uh, have in a, we can say, leaky integrate and fire circuit. So leaky integrate fire circuit is the one that we use to mimic the neurons nowadays. I mean, in the conventional neuron model, using for the spiking neural networks. So this model is also implemented like this. If you see, so if you see this leaky integrate and fire neuron, this is implemented with the help of leaky integrator. So you have an integrator, which is, you can see here, this is op-amp based, and then there is a resistor that is in parallel. This becomes a leaky integrator. And then we have a threshold, which is zero in this case. And you can put a voltage here to get another threshold. So this is the kind of neuron that can be implemented, and it mimics the neuron behavior quite well. And this is called as leaky integrated fire neuron. So if you see here, this will generate an output like this, and the output will go towards the resting state, and then output will go again towards the resting state. And if the spike comes, then we say that if the spike comes, then there will be some voltage that will some current that will flow here, and the current will increase the potential of this particular output, and this is called membrane potential. And as the potential increases with continuous integration, the potential will increase beyond the threshold, and then there will be a spike. So this is how it works, and this particular circuit is called a synapse. Synapse is basically, as I told you before, that is a connection between the axon and the axon and the output. So we can say the connection between two neurons consists of a synapse. If we can say, if we simplify the biology, we can simply say that there are two neurons and they are connected through what we call a synapse. So you have a presynaptic neuron, which is before the synapse, and then you have a postsynaptic neuron, which is after the synapse, and they are connected to a synapse. And synapse is where the data is stored in the form of um, memory, right? So data is stored, and synapse is the memory, and the neuron is the computational unit. So these two together work to perform the computation. So using the new spiking neural networks. So this model is called leaky integrated fire model, where we are using capacitor to mimic the membrane potential, uh, and uh, and then we use a leaky integrator to perform the perform the integration, and then moving toward the resting potential. And then we have one more circuit is required, that is thresholding circuit. So this will be done by a comparator, and then finally you will get the output. So output is a spike that is generated from this particular neuron. So this is, you can say, simplified architecture of neuromorphic. We can say simplified computing architecture, which consists of neurons and synapse. Synapse is the memory, as I should reiterate here, and neurons are the computational units, small computational unit, and there are millions and billions of neurons which are required to, which are there in the brain. So you need, yeah. So, so you need multiple some such neurons to perform the computation inside a spiking neural network. But the main entities are these neurons and synapses. So, yeah, so far I hope that I have covered the background of neuromorphic computing. And now what is important to understand is the how ferroelectric FETs come into picture, and how we can improve the implementation of neuron from this conventional architecture where we use a capacitor, an integrator, and then obviously how we can improve this synapse. Synapse is a memory that is required to store data. So these two things, how we can do using ferroelectric FETs, we'll go one by one. So first, let's discuss about the implementation of Neuron using ferroelectric FETs. And what is ferroelectric FET is also important to understand. So, ferroelectric FETs, if you see here, this is the figure of a ferroelectric FET. This you see that here what we are doing essentially is we are changing this gate stack and incorporating a ferroelectric layer in between, which is called the HFO2 layer or hafnium zirconium oxide layer. This is the doped HFO2 layer, which is doped with zirconium or silicon. And if you see that this HFO2 layer is not there in the conventional CMOS, and in high K metal gate you have this HFO2 layer, but you do not have it as doped with zirconium. So this particular gate, if you incorporate this normal FET becomes a ferroelectric FET. So this is we can say a model of ferroelectric FET. You have a MOSFET, normal conventional MOSFET, and then you have a capacitor, which is called ferroelectric capacitor, and then what is basically this does is now the gate voltage basically gets dropped in this ferroelectric capacitor and the MOSFET gate. So the total will be the overall gate voltage of this particular device. And from here, the charge in the channel will also depend upon these two things, the charge in the ferroelectric and then the charge inside the, we can say, the total is the important. The charge in the channel is controlled by the charge inside this ferroelectric capacitor. And as we see, you see here in this figure, the important thing here is that the threshold of this device can be changed as you increase the gate voltage in this particular direction. So if you see that the threshold voltage is decreasing when you apply polarization, or we can say when we apply some potential at the gate. So this is how ferroelectric FET operates. When you apply a positive potential, that will enhance when you apply a positive potential at the gate, then the polarization of the ferroelectric will be downwards, and then the potential will this will induce charges in the channel, and these charges basically will lower the threshold voltage of the device. And if you have the polarization upwards, it will deplete the channel, and then the potential will increase. So this is how the ferroelectric FET works. It works by modulating or changing the conductance of the channel by using a ferroelectric capacitor at the gate of the transistor. So basically, we are changing the gate stack here to incorporate ferroelectric behavior. One of the important things that we should note is that this particular structure, this also has memory, because you have a ferroelectric, and ferroelectric can be polarized in either up direction or the down direction. So you can store the data, and then also you can perform the logic, because this is an NMOS transistor or transistor, which can also perform the logical operations. So these basically memory and logic are co-located in this particular device. So that's why it is important from the perspective of neuromorphic computing architectures. The memory and the logic are co-located, can be co-located in this particular device. Okay, so the figure is from this paper. You can see this probably if you want. So, so let me just, yeah. So how we can incorporate the neuron in this is very useful to understand now. So if you see that, how do we incorporate a capacitor inside a conventional capacitor can be incorporated in CMOS technology in the form of the metal insulator, metal capacitor, or MIM cap. Now, the problem with MIM cap is that it is not the front end of line compatible. It is back end of line compatible, and obviously we need the integrator to integrate, and we have seen the leaky integrate fire circuit. Now, if you use a ferroelectric FET, then the channel conductance can be modulated with the gate itself. And if you can tune the gate, then you can tune the channel. So basically, you can control the channel through the ferroelectric gate. We can say ferroelectric layer in the gate stack. So in the conventional one, you have this kind of equation where you have linear RC charging, and each input pulse adds charge to the capacitor, and the charge changes by delta Q amount, and this will increase the voltage, and integration is performed using a capacitor. So this that's why basically multiple pulses, when the pulses, or we can say spikes that come, and they cause monotonic voltage rise towards the asymptote. Now, what is important, if similar to this, we can assume that PT, polarization, is the we can say the potential, and sorry, polarization is in the ferroelectric material can be changed, and when the polarization changes, the potential will obviously change, and that gate can be can be called as a membrane potential. And each subcoercive means the pulse that is less than the coercive field of the ferroelectric material, it will rotate the domain incrementally. And when the increment, as you keep on giving some pulse, then the increment will occur, and that integration will be it will be state dependent, which is also great because neuron will have memory, and the threshold behavior emerges naturally from hysteresis. So you have this also in our ferroelectric material. So basically, ferroelectric FET is inherently capable of performing the function of a neuron because of these properties. And this has been also demonstrated in one of the papers by Suman Datta. So this is the Suman Datta is basically and one of the authors, and his group is working on this particular area very aggressively. And so I have taken this next figure from this paper. So I could not keep the reference here because of a lot of things on the slides. So if you see that what will happen here is basically there is a presynaptic neuron. This is a set of presynaptic neurons. This will spike when these spike, then the synapse, or we can say weights will be updated. Weights basically will be stored in memory or synapse, and these synapse will cause a postsynaptic potential change, and they will basically act as input to the postsynaptic neuron, and this is the neuron which has a membrane potential, and this can be mimicked with the help of a ferroelectric FET. So what happens in a ferroelectric FET, if you give pulse inside the gate stack, you have these independent ferroelectric domains, or we can say uniformly polarized areas. So these uniformly polarized volumes, in fact, uniformly polarized volumes, they are going to be used for changing the state of the neuron. And as the spikes will come, these smaller spikes are going to basically go for minor loops. So if you see this particular polarization versus VFE ferroelectric voltage, so if you apply a voltage across this ferroelectric capacitor, you will see this kind of hysteresis kind of behavior. Now, this behavior is typical of ferroelectric materials, but when you incorporate inside the gate stack, and these individual smaller domains change the state, you will also find what is called as minor loops. So you have these minor loops. So these minor loops are where the things will happen. So if you see from the hysteresis diagram, if the polarization changes gradually with pulses, we get analog response, or we can say the polarization, if we are giving pulses like this, one by one, the polarization will increase something like this, and the polarization will keep on increasing as the pulses come. The polarization will keep on increasing, keep on increasing, keep on increasing, keep on increasing. This is like the behavior of integration, and that is happening, and natural relaxation that is present in the ferroelectric material. So, so before the coercive field, the polarization changes gradually with the pulses. Like this is kind of an analog response that happens, and at the coercive field, the slope of the hysteresis loop is nearly vertical. So that this dp by dv goes to infinite. So we can see this at the at this point. This is quite vertical. So basically, if you see after coercive field, the polarization saturates at P up or P down, and this is where we get the digital response, or we can say the memory response. Then this creates a self-generated threshold, because once you are at the coercive field, then the polarization may switch, and the pulses, when accumulate pulses, gradually increase the polarization. And as the polarization approaches plus minus VC or coercive voltage, the small additional pulses can cause rapid change in polarization. And when the coercive field is exceeded, polarization switches abruptly, and this will basically uh, change the state of the ferroelectric material, and when the state is changed, it will lead to a spike which is generated automatically. So all the properties of the, we can say, neuron are integrated in this ferroelectric material, and we do not need explicit threshold circuit. So this all the functions that are involved in the neuron, they are done by the ferroelectric FET independently without using additional devices, because you need a leaky integrator uh, in that particular case where we try to mimic the neuron in a hardware. We need a leaky integrator, and then the comparator also. But all this is not required in this case, because the ferroelectric material and its incorporation in the gate stack inherently does all these things by itself. And that's why it is important to, we can say, we can use ferroelectric neuron and in this particular case. So yeah, so if we compare between the two kind of approaches, one is the capacitor based that we saw, which is the leaky integrator, and using the leaky integrator and comparator, and then one is the FEFET based. This requires a very large area of 100 to 244 micrometer square per neuron. And the FEFET base is much smaller. It may require some additional transistors, depends on the realization, but this is very small, significantly smaller. Then the membrane potential basically uses physical charge on the plates of the capacitor, and the capacitor here is normally the metal insulator, MIM capacitor, when we want to implement in CMOS technology. And if you use the ferroelectric polarization here for the membrane potential storage, then here we have the leak behavior by using the leaky integrator exponential decay. When we put a resistor in parallel, we perform this exponential decay. And the ferroelectric materials have this quasi-lake behavior, but that is history dependent. But since we are not bothered about history here in case of neuron, uh, so this behavior will be there. And the ferroelectric material also shows stochastic. So you go for stochastic neural networks. These are natural from domain dynamics, because the switching does not occur we can say at a deterministic time. It may occur at a range of times, and it happens normally uh, uh, over a period where the probability is maximum. So the switching operation of ferroelectric material is probabilistic in nature. Then power consumption, you have CF square, CV square F, and this is quite low power because we are basically charging and discharging the ferroelectric material, and the transistor is there where the power can be reduced. Then non-volatility is not applicable for a neuron, but yes, non-volatility is present in this FEFET, and scalability is also important. We have, yeah, it is difficult to scale a capacitor because the capacitor area is the dominating factor in this particular type of neuron, and it requires a lot of area. FEFET based is better because there's no capacitor, external capacitor needed, and we can use the hafnium oxide based gate stack to mimic the capacitor itself. But it is also a ferroelectric capacitor, so it is giving further advantages. Then device maturity, this is well established, obviously, because we have MEM caps or metal insulator, metal capacitors present in our CMOS technology. And this is FEFET based is emerging, and we have, I mean, demonstrations at 28 nanometer nodes, and physical demonstrations of ferroelectric FETs has been done. And this has a high integration density, which is FEFET based. So overall, if you see that the conventional method of implementing neurons um, is far inferior as compared to the FEFET-based approach, which we can say, focusing on here in this presentation. Okay, so let me go further and a little bit quickly now because we have some restrictions on time also. So yeah, so just let's start with uh, how does it work? Basically, we use analog, what we have seen. We use analog part where we are emulating neurons, and there can be a digital part also because we cannot survive without digital parts, some digital parts, and we can also have some hybrid parts. And then we can perform by receiving spikes using a memristor crossbar array. And similarly, we can go for communicating the spikes using the different mechanisms. So this is how neuromorphic computing works in physical, um, we can say, realizations that have been done so far, but they are mostly done on R.M.D based systems, resistive random access memory. So if you see the neuromorphic chips that have been developed, they are using the resistive random access memory technology. And the learning, or we can say on chip or off chip or supervised or unsupervised learning, that will take place in this particular part where you are programming the weights and biases. Okay. So yeah, so perceiving and processing spike, this is a complex problem, but people are looking into it. And one of the solution basically is the memristor crossbar array. And this memristor crossbar array is also being looked at as we can say where we use this cross connection of we can say the bit line and the word line to perform the we can say the computation, which is called multiply and accumulate operation or MAC operation. So if you see here, there is a resistance here that is tunable or reconfigurable. So this resistance is reconfigurable, and when we apply a voltage, that voltage multiplies with this to get the scaled value of current here, and this will change with the activation as well as the weight, which is the conductance of this particular element that is between the bit line and the word line. So this is a typical memristic crossbar array that mimics the synapse in the neuromorphic domain. And this is used for matrix multiplications and multiply and accumulate operations. And sending and receiving spikes is quite tedious, and there are still, work going on, and so I will not comment on it much, but because this is time variation is very important, and that's why it is not going to be easy to do it on a chip. So that is what is a challenge in this particular domain. So we cannot have we cannot have a connection between each neuron and each sending neuron and each receiving neuron, and there have to be some programming that has to be done through address encoder and address decoders. And this is managed with some address event representation scheme, but these are just evolving. And yeah, so this is one of the challenges that is there in neuromorphic computing. So many neuromorphic systems use this kind of representation, but this is still a challenging problem, because since this communication is asynchronous and also the network is analog, you have a lot of problems creeping in to this particular domain. So this is how actually this works. If you see that the matrix vector multiplication is inherent. If you have a crossbar array or memristive crossbar array, then these conductance G11, G12, G13 can be programmed. So this matrix can be programmed by changing the weights or conductances of these elements. And this part is basically currently done using R.M. devices uh, in the neuromorphic chips that are built currently. But but of course, there are many options which are emerging non-volatile memories like spin transfer torque memories, and then ferroelectric FETs, which we are going to discuss in the next few slides, how they are basically programmed as different conductances, or this conductance matrix can be changed. And if we incorporate ferroelectric material, ferroelectric FETs here also, that will be advantages. So this is basically what is called as a synaptic crossbar. So this synaptic crossbar is used for as memory or inbuilt memory, where neuron and synapse are co-located. So both memory and we can say memory and the logic is co-located, and then this memory can be reprogrammed to perform a certain task, which is used in machine learning. So and this will give you, we can say, um, the computation directly in the form of we can say weights and biases, adding up weights and biases. So you get addition with a linear combination directly inbuilt in this kind of a resistive or memoristive crossbar array. Okay, so this is we can say a summary of the entire picture of neuromorphic computing. So you have a synaptic device whose state at any given time is not solely determined by the current input, but is also influenced by the past input patterns and the sequence of operations it has undergone. So basically, the synaptic device, if you understand, this is history-dependent behavior is important in this device, because the synapse cannot be implemented using DRAM and SRAM, because this traditional memory do not have are volatile, and they are not history dependent. They basically do not store the history. And that's why it is important to look for the emerging non-volatile memory, like resistive memory devices, phase change memory devices, magnetic tunnel junctions of spintronic based devices, and of course the ferroelectric FETs, right? So the synapses has two important properties which are important. One of them is the long-term potentiation and long-term depression, and the second is synaptic time-dependent plasticity, which is how the time, we can say, time of the spike changes the synapse properties or conductance of the synapse. So yeah, so this synaptic time dependent plasticity is one of the properties, basically that when the presynaptic neuron is spiking and then the postsynaptic neuron is spiking, and both are the inputs to a synapse, then the time difference between them is important. So if the delta t, the postsynaptic neuron spikes first and presynaptic spikes later, then the delta t is less than zero, and the conductance of the synapse should decrease. And when this is positive, the conductance should increase, and that's what happens in a synapse. So you need these properties to be mimicked in a synapse, and this property is called synaptic time dependent plasticity, where the amount of, you can say, difference temporal variation of pre and post synaptic spike, it decides the change in conductance or synaptic weight of the memory element. So these results are from R.M., one of the papers from R.M. So this is not ferroelectric, but the ferroelectric FETs are also having these properties, and these properties, which are basically, we can say, if we simplify to understand this, what is the important property here? It basically means that the synapse has a history-dependent behavior. It its property, which is conductance, it changes with depending on the history of the inputs. Okay, so this these results are from an RM, where you can see a long-term potentiation and long-term depression, where we have these two properties which are mimicked by RM. RM is one of the, we can say, technologies that is CMOS compatible. And if you see the chips which are developed by IBM and other, you can say, Intel and other, which are neuromorphic chips, these are developed using RM technology. So let's see now how the ferroelectric FET comes into picture in this synapse properties, and that is also important to understand, because synapse is where all the programming is going to happen. So the emerging technologies which are used for this synapse are obviously SRAM and DRAM cannot be used because they are conventional memory technology and they do not have a history dependent behavior. Flash memory can not be used because this has lot of time, I mean, lot of excess time. So we can go for some of these, like ferroelectric memory, spin transfer torque memory. And these, one of the important things is the ferroelectric memory. And this can also be used in synapse because it has a memory behavior. And if you see that if you apply electric field, you will find that the polarization of this ferroelectric material changes. And because you have a doped hafnium oxide with zirconium ions, and this zirconium ion can be placed above the center or it can be below the center. And the dipole moment of this molecule or this complex molecule will depend upon the symmetry, or we can say presence of this black zirconium ion. So which is ferroelectric, which makes it ferroelectric in nature. So ferroelectric materials are basically a class of materials which come in dielectric, and dielectric basically has many, we can say, classes: paraelectric, piezoelectric, pyroelectric, and ferroelectric. So inside the paraelectric, you have a ferroelectric also at a certain temperature, which is below the Curie's temperature. So you have these kinds of materials which are there. So yeah, so in the ferroelectric material, what happens is there is we can say the polarization remains even after the electric field is removed. So if E equals to 0, which is here, the polarization is there. If you have polarized it with a positive electric field, some polarization will be left out. And if you are polarized with the negative electric field, some polarization will be left out. And this is what happens in a ferroelectric material. And this is what gives memory to this material. And when it is incorporated in the gate of the FET, then you can incorporate memory in the FET also. So ferroelectricity, probably I'll just go through quickly. So here, as I told you before, that the paraelectric materials, they are centrosymmetric. It means that there is no deviation of this site from the center. And in the non-centrosymmetric structures, this atom basically is either up or down from the center. And that's where the ferroelectric property comes, where the polarization is non-zero at E equals to 0 because of either up or down polarization of the dipole. So, so these individual, we can say, dipoles will together form the polarization in the material, and they will look something like this. When it is polarized in this state, you will get the electric field in this case, but it's polarized in the opposite state. So you have E and P in the same direction, and here you polarize in the opposite state, so you will have in the opposite direction. So you can see that this kind of hysteresis behavior is obtained in the ferroelectric materials. Now, if we compare that, this particular capacitor is also called as ferroelectric capacitor because there is a ferroelectric dielectric in this capacitor, and yeah. So moving further, if you know that the relationship between the capacitance and voltage and charge is this, which is C equals to dq by dV, right? Now, if you know that the energy of the capacitor is energy stored in the inside the capacitor is q square by 2c, right? G is the energy. Then what is capacitance? Capacitance, from here you can find the capacitance, which is basically the d2g by dq2 inverse, right? So this particular value is called capacitance, right? Which is the double derivative of g and inverse of that. Inverse curvature of energy density is called capacitance. Okay. So yeah, so if you see that in a ferroelectric capacitor, you have two minimas in this curve where we have so this is a parabola for normal dielectric. For a negative capacitor, this will be a parabola of inverse nature. But for a ferroelectric material, this is the nature of a energy versus Q. So you can see that here we have what we call as two minimas, where the polarization will be opposite, and then this particular state is called metastable state, where which is not stable, and these two are the stable states where the polarization will be stable. So if so this is from the Landau-Devonshire theory of ferroelectric material. You can look at it more deeply if you want. So basically, the Gibbs free energy is given by this particular expression. This is a complex relationship between the electric field and the polarization, and alpha here is the constant, which is called Landau coefficient, and this depends upon this particular expression where T naught is the Curie's temperature, and if alpha is greater than 0, then obviously you will get the paraelectric material. and if alpha is less than 0, you will get the
basket nilam.
ferroelectric material. So in the paraelectric material, you don't have any polarization, and there is only one stable state for G equals to 0. And in the ferroelectric material, you have multiple states. You can see this multiple states and one metastable state that is there. So these two stable states are for the polarization when electric field is removed. So one of the states will be present. Okay, so that is the case. Now, when the ferroelectric materials they are subjected to the electric field in the normal paraelectric capacitor, or we can say in a capacitor with paraelectric dielectric, you will have this kind of relationship. But in a ferroelectric material, you will get S-shaped curve, and this S-shaped curve is basically between the electric field and the polarization. So this point is the saturation polarization, and this point is the saturation polarization. This point is the remnant polarization, and then this point is the switching is happening here, and this particular slope, which is unstable, in where the opposite, where the we can say you have a negative slope between polarization electric field. This slope is the called the negative capacitance region, and which is unstable. It means you cannot if you yeah. So if you have a ferroelectric capacitor, you will never go into this region because it is unstable. But this region is used for NC-FETs, which is negative capacitance ferroelectric transistors. This is unstable region, but it can be stabilized for in the NC-FETs. So in the NC-FETs, we use a dielectric as well as ferroelectric, and there you basically stabilize this state of ferroelectric material by moving it up. If you add some capacitance in series, you will get like this, and there you will get we can say this kind of a curve which is stable. So you are here, this will be stable. So for the ferroelectric material, and together they will have a single stable point, right? Which is a typical ferroelectric plus dielectric system and used in NC-FETs. So this is yeah, common for negative capacitance field effect transistors, but yeah, obviously we are discussing about ferroelectric FETs, so we do not go use this particular region for ferroelectric FETs. We use these two regions for ferroelectrics, the blue ones. So this one and this one, right? So in the PE curve, we don't have this. We only have these two, right? So yeah, so one of the advantages of ferroelectric materials is also that they are now CMOS compatible. Because when people started to use HFO2 in the hafnium oxide in the high K metal gate devices, or we can say HKMG in 2008, they basically tried to introduce impurities like zirconium, aluminum, silicon, strontium, titanium inside the ferroelectric material, and then that became ferroelectric. So hafnium oxide is inherently dielectric, but not dielectric, paraelectric, but hafnium oxide doped with zirconium becomes ferroelectric in nature because the zirconium ions occupy the non-center, or we can say non-centrosymmetric site of the lattice. So FEFETs are now developed, which are CMOS compatible, and they can be developed with different kinds of stacks. So one of them is called metal ferroelectric semiconductor stack, where we have ferroelectric layer between the gate and the bulk. Then we have metal ferroelectric insulator semiconductor, which is MFIS stack, where we have insulator as well as ferroelectric material. So here basically charge injection can be minimized, and insulator layer provide interface damage during protection, during fabrication, because insulator layer, yeah, it provides protection for the ferroelectric layer. And then we have MIS kind of structure, where the floating metal is provides highly thin ferroelectric film without damaging the SiO2 layer. So this particular stack is also commonly used in ferroelectric FETs. So yeah, so these devices also have inherent memory. You can see that if you apply a positive gate, we have a down polarization, which will enhance the channel, and that's why it will be a low VTH state. And when we polarize it in the positive direction by applying negative potential, that will be high VTH state. And even if the voltage is removed, the VTH state is retained, and that's why it is we can say non-volatile in nature. Then we also have domains inside this ferroelectric material, or we can say groups of atoms that have a uniform polarization. So you can change these individual domains to get the minor loops and change the threshold voltage in steps for different neuromorphic applications because we can program these weights and this when this polarization changes, the conductance of the channel will also change, and this is what we want, and these states can be programmed in multiple ways by applying potentials from you can have multiple states, and that's why they can be used in synapse applications in neuromorphic computing. So these are the important aspects of ferroelectric FETs that are used for neuromorphic applications. And reprogramming and history-dependent behavior is what is important here to make them useful for neuromorphic applications. So yeah, we also did some simulations in our own papers, and we also saw similar properties like we showed using Centaurus TCAT simulations, the long-term potentiation and the long-term depression using these kinds of pulses in our simulations. And we also saw the major loop and minor loop characteristics which are important for neuron applications. You can see the major loops and minor loops when we apply asymmetric kind of inputs to the gate of the ferroelectric FinFET transistors. This is done on a FinFET architecture. So this is from the simulations that we have done. And so finally, I want to finish this talk with a look at some of the products which are available today. And they use some of the components we have seen so far. So so if you see that we have some analog neuromorphic chips like rolls, and Dynaps, which is now commercialized by Synsense Technologies companies. And the basic rolls chip has 256 adaptive exponential integrated fire neurons with 64K synapses. So yeah, and similarly you have chips like NeuroGrid, which has millions of neurons, but the synaptic weights are stored off chip, and you have other chips which are working above threshold, so analog above threshold, and then you have ICANN and brain scales, So these are some of the neuromorphic chips which are there. Then you have digital also. So digital is spin maker, and there are FPGA, sorry, custom ASIC like True North by IBM. So these are the different neuromorphic chips which are available, and Lohi by Intel. So this is also a neuromorphic chip that is available. Yeah, but as I told you, these are conventional ones which use CMOS, and some of them use RM, and they are not using FEFETs as of now. But this is an emerging technology that is being explored for neuromorphic architectures. So with this, I will conclude my presentation, and yeah. So of course, I will be open to questions if you have. Yes, if you have any questions, please ask me. And first of all, I would thank the organizers for yeah, mm, for inviting me to this particular presentation. And if there are any questions, I will be happy to answer.
Thank you so much, sir, for your presentation. Participants, if you have any doubts, you can either unmute yourself and you can ask, or you can post it in the chat box too. Um, Thank you so much, sir. Shall I share your number if any of the participants